Imagine the scene. November 1918. Across the European continent, engineers wrestled with a formidable dilemma. The cataclysmic Great War had concluded, yet its most stark revelation was etched into every pockmarked battlefield, from the bloody fields of Verdun to the devastated landscapes of the Somme. Conventional wheeled transport alone could no longer secure victory in modern warfare. Lorries frequently became mired in the quagmire, tanks suffered constant mechanical failures, and somehow, armies still desperately needed to convey personnel and armaments across terrains that resembled the desolate, cratered surface of the moon. It is precisely within this peculiar intersection between two disparate concepts that seemingly defied integration but absolutely had to converge that our compelling narrative truly commences. The innovative concept of the half-track did not materialize spontaneously from a void. Indeed, its genesis can be traced back to 1915, when a gifted French engineer named Adolphe Cagrès was employed by Tsar Nicholas II in Russia. His primary objective was to ensure the continued mobility of the imperial family's fleet of automobiles through the formidable, snow-choked expanses of Siberia. Cagrès' ingenious solution involved replacing the vehicle's conventional rear wheels with flexible rubber tracks, while retaining the front wheels for crucial steering capabilities. This design was remarkably simple, undeniably brilliant, and, most importantly, demonstrably effective. By 1919, the renowned French automotive manufacturer Citroën had acquired Cagrès' patents and commenced production of the Cagrès-Hinton system, conclusively demonstrating that this innovative hybrid approach could effectively navigate challenging topographies that proved insurmountable for purely wheeled conveyances. However, at this nascent stage, military applications were not yet under consideration. The primary focus remained on prosaic civilian utility, facilitating travel from one point to another when natural conditions presented severe obstacles. After 2 or 3 paragraphs, ask us to stay with us and watch the end of the video. We will be grateful for your like and subscription. As the 1920s unfolded, military strategists began to pose increasingly uncomfortable and pertinent questions. Tanks, while undeniably potent instruments of war, were agonizingly slow. A British Mark V, for instance, could barely achieve a speed of approximately 4 miles per hour on an exceptionally favorable day. Trucks, conversely, offered commendable speed but proved utterly useless the moment they ventured beyond the confines of paved roadways. Infantry divisions continued their arduous marches on foot, much as they had during the Napoleonic era, a stark reality that meant armored formations would often surge ahead, only to be compelled to halt and await the arrival of their rifle-wielding comrades. Even the Germans, despite their recent defeat in the Great War, were already meticulously sketching out nascent design ideas. The Soviets, too, were actively engaged in experimental endeavors. Furthermore, the Americans, who had made only minimal use of tanks during World War I, initiated their own exploratory tinkering with various designs at the esteemed Aberdeen Proving Ground. The profound allure of the half-track lay in its audacious engineering compromise. This ingenious design offered approximately 70% of a tank's formidable off-road prowess, while simultaneously preserving roughly 80% of a truck's superior speed and inherent mechanical simplicity. The presence of front wheels afforded respectable steering capabilities, obviating the need for complex track braking systems. The rear tracks, meanwhile, judiciously distributed the vehicle's substantial weight across treacherous mud, shifting sand, or deep snow. Moreover, because power was not exclusively directed to all 4 corners via tracks, the entire assembly remained lighter, more economical to produce, and considerably simpler to maintain than a full-fledged tank. In 1931, the United States Army conducted tests on the Cunningham T1, essentially a conventional truck with tracks unceremoniously affixed to its rear. While its appearance was undeniably ludicrous, it astonishingly traversed trenches that would have completely immobilized ordinary trucks. By the mid-1930s, the stark realities of an evolving geopolitical landscape were becoming increasingly manifest. Germany was clandestinely rearming, brazenly circumventing the stringent restrictions imposed by the Treaty of Versailles. Japan was aggressively expanding its territorial influence into China, deploying formidable mechanized columns. The Spanish Civil War, which raged from 1936 to 1939, served as a crucial proving ground where all belligerents absorbed the same brutal truth. Modern warfare necessitated infantry forces capable of maintaining pace with armored units, and crucially, they needed to arrive at the battlefront prepared for engagement, not utterly exhausted from a grueling 20-mile march. The half-track was no longer merely a clever mechanical contrivance. It was rapidly transforming into an indispensable military imperative. Engineers in industrial centers such as Detroit, Stuttgart, and Moscow found themselves in a relentless race to solve an identical, pressing enigma: how to construct a vehicle that could fight like a tank, haul like a truck, and deliver firepower akin to artillery, all while maintaining a production cost reasonable enough to facilitate the manufacture of tens of thousands of units. This pivotal question would ultimately define the formidable machines that rolled into Poland, France, North Africa, and eventually across half the globe. The era of the hybrid warrior was unequivocally about to commence its baptism by fire. The Americans approached the intricate half-track design challenge with a characteristic preoccupation that defined their industrial ethos in the 1930s, an unwavering focus on mass production from the very outset. While their European counterparts meticulously crafted bespoke, often elaborate, solutions, engineers at the White Motor Company in Cleveland and Autocar in Pennsylvania were already envisioning vast assembly lines capable of churning out vehicles by the thousands. The culmination of this pragmatic vision was the M2 and M3 half-track family, machines that presented a deceptively brutish simplicity on their exterior, but concealed genuinely ingenious engineering beneath their boxy, utilitarian steel panels. At the core of these American half-tracks lay their power plant. The White Motor Company ultimately settled upon the Hercules JXT inline six-cylinder engine, a robust 386 cubic inch gasoline motor that generated a respectable 147 horsepower at 2,800 revolutions per minute. While this output might seem modest when compared to contemporary engines, its crucial advantages were multifaceted. It demonstrated exceptional reliability, could be manufactured with impressive speed, and, significantly, mechanics already familiar with civilian trucks possessed the requisite knowledge to service and repair it. The engine was conventionally positioned at the front, mirroring standard truck design, which facilitated straightforward heat management and allowed for accessible maintenance without requiring the dismantling of the entire vehicle. Maximum road speed reached an impressive 45 miles per hour, diminishing to approximately 25 miles per hour cross-country, contingent upon the specific terrain. This speed was sufficiently swift to keep pace with tank columns, yet not so excessive as to render the ride a jarring, bone-rattling ordeal for the 10 infantry soldiers typically accommodated in the rear compartment. The transmission system was where the white engineers truly distinguished themselves and justified their considerable efforts. They meticulously developed a 4-speed manual gearbox complemented by a 2-speed transfer case, furnishing the driver with a comprehensive total of 8 forward gears, in addition to 2 reverse gears. This extensive range empowered the vehicle to ascend a challenging 60% grade in its lowest first gear, or effortlessly cruise at highway speeds in its highest fourth gear. Power was efficiently routed from the transmission to a front axle, driving the wheels, and a separate drive shaft extended rearward to the track assembly. The front wheels retained their conventional pivoting capability for steering, but here resided a particularly clever innovation. The driver also had access to independent brake pedals that could selectively slow individual tracks, enabling significantly sharper turns than the front wheels alone could achieve. While mastering this intricate control required considerable skill, experienced drivers could effectively pivot these formidable machines almost in place. Now, turning our attention to the track system itself, this component truly epitomized American pragmatism. Rather than utilizing metal links, akin to traditional tank treads, the M2 and M3 half-tracks employed innovative rubber block tracks developed by the Firestone Tire and Rubber Company. Each track was ingeniously constructed from steel cable embedded within a durable rubber matrix, onto which 110 individual rubber blocks were vulcanized. These blocks, roughly 5 inches wide, were meticulously shaped to provide superior grip on dirt, mud, or snow. The brilliance of this design was threefold. Firstly, rubber inherently produced less noise than metal clanking against metal, a crucial tactical advantage for stealthy movement. Secondly, rubber exhibited greater longevity on paved roads, avoiding both the damage to highway surfaces and the rapid wear experienced by metal tracks over short distances. Thirdly, in the event of localized damage, individual blocks could be replaced in the field, eliminating the need to swap out entire track assemblies. The suspension system incorporated a modified vertical volute design, essentially comprising large coil springs mounted vertically behind each of the 4 road wheels on every track assembly. As the vehicle traversed obstacles, these springs compressed, effectively absorbing the shock. Was the ride smooth? Not particularly. Traveling in the rear of an M3 over rugged terrain was often likened to being inside a cement mixer, yet the system was undeniably effective. It proved simple to maintain and, most crucially, it efficiently distributed the vehicle's substantial 20,000-pound combat weight across a sufficient surface area to maintain ground pressure at approximately 10 pounds per square inch. For context, a fully loaded conventional truck might exert up to 40 psi, which elucidates why trucks often became mired in mud, while half-tracks maintained their mobility. Production accelerated at an astonishing rate once America formally entered the war in December 1941. The White Motor, Autocar, and Diamond T plants were collectively churning out 500 half-tracks per month by mid-1942, escalating to an impressive 1,500 units per month by 1943. Total production ultimately surpassed 41,000 units across all variants by 1945. This remarkable output underscores the genius of the American approach. These machines may not have been the most technically advanced half-tracks ever conceived, but they were sufficiently capable, and crucially, tens of thousands of them were rolling off assembly lines precisely when the Allied armies desperately required them. While American engineers meticulously designed for unparalleled mass production, their German counterparts were consumed by an entirely different obsession, achieving technical perfection, irrespective of the associated cost. The SD, KFZ 251, more popularly recognized as the Hanomag after its principal manufacturer, embodied a fundamentally opposing philosophical approach. Where the Americans pragmatically declared, "Good enough is good enough," the Germans steadfastly maintained that every mechanical component must be engineered to its absolute theoretical limit. This unwavering pursuit of excellence rendered their half-tracks extraordinarily capable on the battlefield, yet simultaneously made them absurdly intricate and costly to construct. the very heart of the SD, KFZ 251 was a Maybach HL42 KRM 6-cylinder gasoline engine, which generated 100 horsepower, a figure notably less than its American Hercules counterpart. However, the intriguing detail lies in its lineage. Maybach was the very same prestigious company responsible for fabricating the formidable engines powering the Tiger and Panther tanks. Consequently, this was no mere truck motor repurposed for military service. The HL42 was meticulously engineered specifically for tracked vehicles, with scrupulous attention paid to optimizing torque delivery at lower RPMs. This powerful engine propelled the 8.5-ton vehicle to a top speed of 53 km per hour on paved roads, actually surpassing the American M3's speed, although its cross-country performance remained nearly identical, hovering around 20 to 25 km per hour. The Maybach engine operated with greater thermal efficiency and cooler temperatures than its American equivalent, but it demanded more frequent, meticulous maintenance and relied upon precision machine parts that invariably required extended manufacturing times. German transmission engineering bordered on what many might consider over-engineering. The SD, KFZ 251 employed a sophisticated Maybach Vari-Rex 128H preselector gearbox, boasting 7 forward speeds and 3 reverse gears. Consider the implications of that. 7 distinct forward gears. The driver would first preselect the desired next gear using a lever, then momentarily tap the clutch, at which point the transmission would automatically execute the shift via an intricate vacuum system. When functioning optimally, this system delivered a smoother and faster shifting experience than the American manual transmissions. However, when it inevitably malfunctioned, which regrettably occurred with greater frequency, it necessitated the expertise of a highly specialized mechanic and replacement parts that could, at times, take weeks to procure. This encapsulates the German half-track story in microcosm. Technically superior, yet logistically a veritable nightmare. Stay with us and watch the end of the video. We will be grateful for your like and subscription. I am from your country/region, and I found the video topic about the evolution of half-tracks to be incredibly insightful, particularly the detailed comparison between the American and German engineering philosophies. It's fascinating how two nations, facing similar military challenges, arrived at such divergent solutions, one prioritizing mass production and reliability, the other absolute technical perfection, each with its own set of advantages and drawbacks in the crucible of war. The logistical challenges presented by Germany's SD, KFZ 251 half-track were indeed formidable, bordering on a nightmare. Its track system, for instance, offered a profound insight into the German engineering philosophy. Unlike the American half-tracks that typically employed rubber blocks integrated into a cable system, the SD, KFZ 251 utilized metal track links, precisely mirroring the design of tank tracks, albeit in a more slender form. Each side of the vehicle was equipped with 70 such track links, meticulously crafted from manganese steel and featuring grooves to enhance traction. While these robust tracks demonstrated exceptional durability on various terrains and could endure considerable abuse, they were notoriously loud, caused significant wear and tear on paved surfaces, and demanded constant adjustment and upkeep. The Germans willingly accepted these compromises, recognizing that metal tracks provided superior performance in the most severe environments, such as deep mud, heavy snowfall, and extreme cold, where rubber components were prone to cracking and failure. However, it was the innovative interleaved road wheel system where German engineering truly distinguished itself. Most half-tracks, including those developed by the Americans, incorporated 4 or 5 road wheels per side, mounted on straightforward suspension arms. In stark contrast, the SD KFZ 251 boasted 7 overlapping road wheels on each side, ingeniously arranged to interlace with one another when viewed from the front or rear, creating a distinctive zigzag pattern across the track width. This sophisticated interleave configuration facilitated a more even distribution of the vehicle's weight, further diminishing ground pressure, and consequently provided an exceptionally smooth ride for a tracked vehicle. German soldiers, who had experienced both captured American half-tracks and their own Hanemags, consistently expressed a preference for the German suspension, attesting to its genuinely superior performance. The inherent drawback, however, was that these intricate interleaved wheels presented a maintenance nightmare. Should an inner wheel suffer damage or require replacement, multiple outer wheels first had to be painstakingly removed. Furthermore, mud, snow, and ice frequently became compacted between the wheels, freezing solid overnight, particularly on the unforgiving eastern front where temperatures plummeted to -40°C. German crews often spent hours each morning armed with hammers and blowtorches, simply to free the wheels. A task that might take a mere 15 minutes on an American half-track could easily consume half a day on a Hanemag. Please stay with us and watch the end of the video. We will be grateful for your like and subscription. Please write a comment about where you are from and what you think about the video topic. The production complexity mirrored the mechanical intricacy. The construction of an SD KFZ 251 in 1940 demanded approximately 3,000 hours of skilled labor, a stark contrast to the roughly 800 hours required for an M3 half-track. Throughout the entire conflict, Germany managed to produce around 15,500 SD KFZ 251s, an impressive feat given their industrial circumstances, yet still less than a third of American production. This disparity eloquently illustrated the German prioritization of quality over sheer quantity, a philosophy embodied in their steel and rubber. Now, the narrative takes a fascinating turn. Someone gazed upon these essentially glorified trucks and conceived the audacious idea of integrating artillery pieces onto them. This concept, initially sounding rather outlandish, gains clarity when one recalls the fundamental challenge of conventional artillery. Traditional towed artillery, reliant on trucks or horses for movement, suffered from protracted setup times and an almost insurmountable difficulty in rapid repositioning to evade counter-battery fire. By directly mounting such a weapon onto a half-track, an immediate transformation occurred, yielding mobile firepower capable of swift engagement, relocation, and enhanced survivability. Nevertheless, the engineering hurdles associated with this endeavor were absolutely brutal. The primary obstacle was the immense recoil, which threatened to utterly destroy the vehicle. When a 75 mm gun discharges, it generates approximately 15 tons of rearward force in a mere fraction of a second. This colossal energy demands dissipation. Simply bolting a cannon to a half-track's cargo bed would inevitably result in the vehicle being torn apart or violently flipped backward. American engineers, working on the M3 gun motor carriage in early 1941, addressed this formidable challenge through a multi-pronged approach. They affixed a French 75 mm gun onto a reinforced pedestal, which was directly welded to the vehicle's robust frame, rather than its less structural body. Furthermore, they incorporated substantial recoil cylinders, essentially hydraulic shock absorbers, that permitted the gun barrel to slide backward approximately 2 feet upon firing. This ingenious mechanism transformed the violent 15-ton impact into a more manageable, sustained push distributed over a full second. Yet, the physics continued to present further challenges. Newton's third law dictates that every action elicits an equal and opposite reaction. Consequently, even with sophisticated recoil management, the act of firing still caused the entire vehicle to rock significantly. The ingenious solution involved the implementation of outriggers and spades, metal struts that could be deployed from the sides and rear, featuring flat plates at their extremities designed to dig firmly into the ground. Before engaging a target, the crew would extend these stabilizers, effectively anchoring the half-track in position. The M12 gun motor carriage, which featured a formidable 155 mm howitzer mounted on a modified M3 chassis, possessed a massive spade at its rear that absolutely had to be driven into the ground prior to each firing mission. Without this critical stabilization, the sheer force of firing would literally propel the 26-ton vehicle backward by several feet with every single shot. The Germans, in contrast, adopted a distinct strategy with their SD, KFZ 251/9 variant, which incorporated a short-barreled 75 mm gun within a limited traverse mount. Instead of striving to create a fully mobile artillery piece, they essentially developed an assault gun, a vehicle designed to accompany infantry, deliver close-range destructive fire against bunkers or buildings, and then rapidly advance. The restricted traverse mechanism minimized structural stress, as the gun could not pivot widely enough to destabilize the vehicle. Its maximum elevation was a mere 20 degrees, indicating that it was not intended for lobbing shells over obstacles. Rather, it was optimized for direct fire at visible targets, typically within an 800-meter range. Ammunition storage also evolved into another logistical nightmare. A conventional artillery piece might have its ammunition carefully stacked nearby in a secure, protected location. On a half-track, however, every single shell travels directly with the vehicle, rendering armor protection absolutely crucial. The M12 GMC, for instance, could only accommodate 10 rounds of 155 mm ammunition internally, primarily due to each shell's considerable weight of 95 pounds and the substantial space it occupied. These vehicles typically operated in conjunction with an accompanying M30 cargo carrier half-track, which followed closely behind, laden with an additional 40 rounds. German vehicles encountered similar constraints. The SD, KFZ 251 out of 9 could carry only 52 rounds of 75 mm ammunition, meticulously stored in bins along the hull's sides where the armor was thickest. Anti-aircraft variants pushed the boundaries of engineering even further. The M16 multiple gun motor carriage, for example, featured 4.50 caliber machine guns mounted within an electrically powered turret, thus creating a highly mobile anti-aircraft platform. The entire turret system, including its integrated generator, exceeded a ton in weight and was positioned high on the vehicle, significantly impacting its center of gravity. Engineers were compelled to incorporate counterweights and slightly widen the track stance to prevent the vehicle from overturning during aggressive turns. The combined rate of fire reached an impressive 2,400 rounds per minute, a figure that sounds formidable until one considers that this equates to 200 pounds of ammunition expended per minute. The M16 carried a total of 5,000 rounds, providing approximately 2.5 minutes of continuous firing before depletion, meaning that the majority of the interior space was dedicated solely to boxes of linked ammunition. Perhaps the ultimate embodiment of this concept was the SD, KFZ 251/22, which the Germans developed in 1944. This variant mounted a potent 75 mm PaK-40 anti-tank gun, a weapon capable of penetrating 100 mm of armor at 1,000 meters, thereby posing a significant threat even to formidable Soviet T-34 tanks. However, installing such a powerful gun on a relatively light vehicle necessitated compromises across the board. Ammunition capacity plummeted to a mere 19 rounds. The gun shield was kept to a minimum, as any additional armor would have overloaded the chassis, and firing from anything other than perfectly level ground risked capsizing the vehicle. Crews quickly learned the critical importance of careful positioning, understanding that their initial shot might be their sole opportunity before having to relocate or face obliteration from retaliatory fire. Tank destroyers represent the pinnacle of desperation engineering. By 1942, both the Allied and Axis powers found themselves confronting tanks for which they had not adequately planned. German Tiger tanks that effectively shrugged off the majority of Allied armaments, Soviet T-34s that overwhelmed German defensive positions, and Japanese armor in the Pacific that demanded far greater firepower than standard infantry rifles could deliver. The core problem was straightforward. Constructing entirely new tanks required time and resources that were simply unavailable. However, mounting existing anti-tank guns on readily available half-track chassis offered a viable solution that could be implemented in months rather than years. The American M3 gun motor carriage was, quite literally, the inaugural attempt, hastily assembled in 1941 even before the attack on Pearl Harbor. Engineers at the Aberdeen Proving Ground took standard M3 half-tracks, removed the bench seats from the rear compartment, and mounted a 75mm M1897 gun, a design actually dating back to World War I, on a pedestal within the cargo area. There was no turret, nor any substantial protection, merely a gun shield and a fervent hope. The 5-person crew remained completely exposed from the waist up. Yet, what truly mattered was its capability. It could effectively destroy German Panzer IIIs and early Panzer IVs at a range of 1,000 yards. And a remarkable 2,200 of these vehicles were manufactured between 1941 and 1943. These vehicles saw their first combat in North Africa, commencing in November 1942, where American forces at Kasserine Pass endured brutal lessons regarding the superiority of German armor. The M3 GMC's performance in Tunisia starkly highlighted the fundamental flaw of the half-track tank destroyer. It possessed the ability to inflict damage, but utterly lacked the capacity to absorb it. Its armor, a meager 6.35mm on the sides, was barely sufficient to stop rifle rounds, and utterly useless against anything heavier. German gunners swiftly recognized M3 GMCs as high-priority targets. Eliminating one early in an engagement significantly neutralized a serious threat. American after-action reports from the battles around Sidi Bouzid in February 1943 unequivocally demonstrated that M3 GMCs were compelled to fire from concealed positions at least 1,200 yards away, continuously utilized their mobility for repositioning, and, crucially, never allow themselves to be caught in the open. They were quintessential ambush predators, not brawlers suited for direct confrontation. The German military, recognizing the need for agile ground combatants rather than heavy-hitting brawlers, found themselves compelled by late 1943 to develop their own half-track tank destroyers on the Eastern Front. The sheer volume of Soviet tank production was relentlessly eroding German defensive postures. Initially, the SD, KFZ, 251/10, armed with a 37mm PaK-36, proved woefully inadequate, its rounds barely capable of scoring superficial damage against the formidable frontal armor of AT-34. This pressing inadequacy spurred German engineers to hastily conceive the SD, KFZ, 251-22, a more potent variant equipped with the 75mm PaK-40, the identical cannon featured on their specialized tank destroyers. Manufacturing commenced in 1944, with approximately 175 units being fabricated before the cessation of hostilities. This new iteration genuinely posed a credible threat to Soviet armored vehicles, boasting impressive penetration capabilities of 133 mm at a range of 500 meters with standard ammunition, sufficient to pierce the hull or turret of a T-34 across most engagement distances. Nevertheless, integrating such a formidable weapon system onto a half-track chassis introduced substantial compromises. The Pak-40 itself constituted a considerable mass, weighing 1,425 kilograms, or over 3,100 pounds. When factoring in the mounting apparatus, protective shield, and a full complement of ammunition, the total combat payload approached 2 tons, a significant burden for a vehicle originally conceived for infantry transport. Consequently, the SD, KFZ 251-22 suffered from a pronounced nose-heavy imbalance, exhibiting poor handling characteristics, and its suspension system was perpetually subjected to undue stress. Its maximum velocity plummeted to 40 km per hour, and its performance across varied terrain visibly deteriorated. German crews frequently articulated that operating a fully laden SD, KFZ 251-22 was akin to grappling with an obstinate equine. Steering demanded immense physical exertion, particularly when traversing muddy or snow-covered landscapes. Over time, tactical deployment strategies for these vehicles evolved through arduous practical experience, leading both American and German military doctrines by 1944 to converge on similar operational principles. These half-track tank destroyers demonstrated optimal effectiveness when deployed within meticulously prepared defensive positions, where they could exploit the natural topography for concealment and protection. Their operational mandate involved engaging adversary armor at the maximum possible range, followed by a swift withdrawal after delivering their salvos. For instance, during the monumental Soviet offensive operation that commenced in June 1944, German SD, KFZ 251-22s were typically deployed in modest formations, usually comprising 3 to 5 vehicles, strategically positioned within treelines or behind earthen embankments. Their modus operandi was to patiently await the approach of Soviet armor columns to within an 800-meter radius, unleash a concerted volley of fire, and then immediately relocate to pre-designated alternate firing positions. Their continued survival hinged entirely upon their mobility and the element of surprise. Engaging in a protracted firefight invariably led to their destruction. We invite you to remain with us and view the entirety of this video. Your appreciation through a like and a subscription would be greatly valued. Please also take a moment to share your geographical origin in the comments section and offer your thoughts on the subject matter discussed in this presentation. Across the Atlantic, the American experience in France following D-Day mirrored these patterns of employment. M3 GMCs played a crucial role in supporting infantry advances, often providing critical overwatch from elevated ridgelines, primed to intercept German counterattacks. During the fierce engagement surrounding St. Lo in July 1944, M3 crews honed their skills in collaborative tactics with M10 tank destroyers. The half-tracks would strategically draw German armor into revealing their positions, thereby enabling the more heavily armed M10s to deliver the decisive blows. This was undeniably perilous work, frequently resulting in substantial casualties, yet it proved instrumental in preventing German armored units from overwhelming American infantry formations. Ultimately, the half-track tank destroyer was never conceived as the quintessential solution. Rather, it represented the most readily available and expedient option. Its rapid production and widespread deployment were necessitated by the grim alternative, confronting enemy tanks armed with little more than bazookas and sheer determination. By late 1944, both Allied and Axis forces were progressively phasing out these improvised vehicles in favor of purpose-built armored platforms. However, for a crucial 2-year period, these hybrid machines admirably filled a desperate and significant void in combat capabilities. Beyond their weaponry and any associated combat glory, the fundamental purpose of the half-track was to transport infantry to the front lines, ensuring their arrival alive and prepared for immediate engagement. This objective, deceptively straightforward, becomes remarkably complex when delving into the intricate engineering considerations. The design of an armored personnel carrier inherently demands a delicate equilibrium between 3 intrinsically conflicting attributes: protection, carrying capacity, and mobility. Excessive armor inevitably renders the vehicle too ponderous for effective movement. Accommodating too many soldiers sacrifices crucial space for ammunition or essential equipment. Conversely, an exclusive focus on speed invariably exposes the occupants to catastrophic casualties upon the first volley of enemy machine gun fire. The M3 half-track's armor configuration precisely illustrates the practical compromises inherent in these design calculations. Its front plate consisted of 12.7 mm of rolled homogeneous steel, strategically angled at 30 degrees. Through the inherent principles of sloped armor physics, this configuration conferred an effective protective equivalence of approximately 15 mm of vertical armor. Such protection proved sufficient to thwart standard 7.92 mm German rifle rounds at a range of 100 meters, as well as .30 caliber machine gun fire across most combat distances. However, the side armor was significantly thinner, measuring just 6.35 mm, providing only marginal defense against pistol rounds and shrapnel, but little else. The rationale behind this reduced thickness warrants examination. Each additional millimeter of steel extending across the vehicle's 18-foot length contributed hundreds of pounds to its overall mass. Engineers meticulously calculated that 6.35 mm side plating represented the absolute minimum necessary to afford crew members and passengers a reasonable degree of safety from fragmentation and small arms fire, while simultaneously ensuring the vehicle remained sufficiently lightweight to retain its vital mobility across challenging, soft terrain. The internal arrangement of the M3 was characterized by its stark practicality. The driver and vehicle commander occupied individual seats in the forward section, each protected by armored doors designed to swing open. Directly aft of their positions, the cargo compartment spanned an approximate width of 6.5 feet and a length of 10 feet, featuring bench seating along both lateral walls. 10 infantrymen would sit facing inwards, their knees often nearly touching, with their rifles either held vertically or resting across their laps. This constricted configuration served a critical purpose. It kept the soldiers positioned beneath the protective height of the armored sidewalls. To stand upright meant exposure from the chest upwards, rendering one vulnerable to everything from rifle fire to debilitating shrapnel. Consequently, combat-hardened units swiftly adopted the practice of remaining seated until the absolute final moment before dismounting into action. The controversial open-top design sparked incessant debate, both during its operational tenure and in subsequent historical analysis. The question of why a roof was not incorporated is addressed by 3 principal considerations: weight, visibility, and egress. A steel roof robust enough to provide any meaningful ballistic protection would have augmented the vehicle's mass by at least 800 pounds, thereby pushing it beyond its design suspension limits and dramatically escalating its ground pressure. More critically, the infantry squad leader required an unobstructed panoramic view of the surrounding environment during movement to maintain situational awareness. Fully enclosing the vehicle would have meant navigating blindly into potential ambushes. Furthermore, in the event of striking a mine or sustaining a catastrophic hit, an open top afforded soldiers the crucial ability to rapidly evacuate in mere seconds, rather than struggling to squeeze through constricted doors while the vehicle was ablaze. The true revolutionary impact, however, resided in the evolution of mechanized infantry doctrine, marking the point where the half-track transcended mere engineering to fundamentally reshape the very nature of warfare. Prior to 1940, infantry units either endured arduous marches or were transported in vulnerable, unarmored trucks, invariably arriving at battlefields either physically exhausted or dangerously exposed. The advent of the half-track forged a novel tactical capability: infantry formations that could maintain pace with armored columns, arriving at their objectives fresh and fully prepared for immediate engagement. During the pivotal North African campaign at El Alamein in October 1942, British and Commonwealth forces effectively utilized American-supplied M3s to follow closely behind their armor. Breakthroughs, swiftly exploiting gaps in enemy lines before German defenders could re-establish their positions. The infantry arrived invigorated and fully equipped, capable of dismounting and immediately securing critical objectives that tanks alone could not hold. The brutal conditions of Normandy on June 6, 1944, provided an even more rigorous validation of this concept. American armored divisions deployed M3 half-tracks to push inland from the landing beaches, transporting infantry through the challenging hedgerow country where tanks were particularly susceptible to ambush. The standard operational procedure typically involved half-tracks advancing in column formation, positioned approximately 50 to 100 yards behind Sherman tanks. When enemy fire erupted, the Shermans would immediately engage the threat, while infantry rapidly dismounted from their half-tracks, utilizing the bulk of the vehicles for immediate cover. This entire sequence, from initial contact to infantry deployment and movement, often transpired within a mere 15 seconds. German after-action reports from the Normandy campaign consistently highlighted the markedly superior speed with which American mechanized units could react to contact, in stark contrast to their own truck-borne infantry, who were compelled to dismount at a greater distance and advance on foot. The sheer numerical integration of these vehicles powerfully illustrates their strategic significance. A typical American armored infantry battalion in 1944 comprised 3 rifle companies, each consisting of 3 platoons, with each platoon containing 4 squads. This organizational structure amounted to a total of 36 squads, necessitating 36 half-tracks, supplemented by additional command and support vehicles, culminating in an approximate total of 50 half-tracks per battalion. These vehicles did not merely transport soldiers. They also carried vital .50 caliber machine guns, mortars, ammunition, radio communication equipment, and essential medical supplies. The half-track fundamentally transformed infantry from traditional foot soldiers into highly mobile mounted troops, thereby revolutionizing the tempo and adaptive capacity of mechanized warfare. By 1945, the strategic inquiry had shifted from whether to mechanize infantry to how to design and construct the next generation of vehicles that could execute this role with even greater efficacy. The deployment of a machine meticulously engineered in Cleveland for the battlefields of Europe into the harsh realities of the Russian winter or the dense jungles of the Pacific theater invariably caused every initial engineering assumption to unravel. The genuine crucible for the half-track was not the control-proving grounds in Maryland, but rather the bone-chilling -40 mornings outside Stalingrad and the oppressive 100% humidity of jungle trails in New Guinea. These extreme environmental conditions necessitated unforeseen field modifications that the original engineers could never have predicted, resulting in the creation of numerous variants that bore only a faint resemblance to the initial designs. The Eastern Front, in particular, proved to be the ultimate test of combat readiness, where the rubber met reality in the most unforgiving manner imaginable. German SD, KFC 251s began experiencing catastrophic operational failures during the severe winter of 1941 to 1942 as Army Group Center relentlessly advanced towards Moscow. The intricately designed interleaved road wheels, initially lauded for providing an exceptionally smooth ride, tragically transformed into perilous death traps when the pervasive mud froze solid overnight between the wheel components. Crews resorted to desperate measures in an attempt to alleviate this crippling issue, trying everything from igniting fires beneath their vehicles to pouring precious gasoline between the wheels and setting it ablaze, and even employing explosive charges to dislodge the stubborn ice. However, none of these improvised solutions proved consistently effective. German field workshops eventually began welding steel plates over the gaps between the wheels, a modification that, while diminishing overall performance, successfully prevented the accumulation of ice. By late 1942, factory production lines had incorporated these lessons, integrating wider wheel spacing and a simplified suspension design specifically tailored for units operating on the brutal Eastern Front. The journey of American M3 half-tracks to the Soviet Union, facilitated by the Lend-Lease program, introduced a distinct set of operational challenges. Between 1942 and 1945, the Soviet forces acquired around 1,000 M2 and M3 models, prompting their mechanical teams to undertake immediate and extensive modifications. A paramount concern revolved around their cold start reliability. The Hercules engine's carburetor proved highly susceptible to freezing in the frigid sub-zero conditions prevalent on the Eastern Front, rendering ignition practically unachievable without considerable and time-consuming preheating procedures. To mitigate this, Soviet repair facilities ingeniously integrated engine block heaters, meticulously insulated fuel lines, and re-engineered carburetors with adjusted jet sizes to better manage the denser, cold-affected gasoline. Furthermore, they constructed rudimentary yet highly functional wooden coverings for the open cargo compartments, thereby converting these exposed personnel carriers into enclosed vehicles. This adaptation offered crucial, life-saving sanctuary against the biting wind chill during protracted troop movements across the vast Soviet landscape. Navigating deep snow presented an entirely different, indeed radical, set of demands on track performance. The conventional rubber block tracks were particularly problematic. They would rapidly accumulate snow, which would then compact into solid ice, leading to a complete and catastrophic loss of traction. Both German and Soviet military engineers sought to overcome this by experimenting with Graussers, robust metal cleats designed to be bolted onto the existing track blocks, functioning much like specialized climbing crampons to bite into the treacherous snow and ice. German ingenuity, in particular, led to the creation of the Winter Kit, a system of specialized track extensions. These extensions dramatically augmented the track surface area by close to 40%, consequently reducing the ground pressure to such a degree that the vehicles could effectively traverse snowdrifts deep enough to completely engulf standard wheeled transport. While the installation of these kits demanded arduous hours of labor under brutally freezing conditions, those units neglecting this crucial preparation prior to winter offensives frequently discovered their vehicles rendered immobile within a mere matter of days, highlighting the necessity of such extreme adaptations. After 2 or 3 paragraphs, ask US to stay with US and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. In stark contrast, the Pacific Theater unfolded a vastly different yet equally formidable array of environmental adversities. The relentless combination of intense heat and pervasive humidity wreaked havoc on sensitive electrical systems, instigated rapid corrosion of metallic components, and transformed vehicle interiors into suffocating saunas, capable of inducing severe heat exhaustion in personnel within minutes. American military contingents deployed to New Guinea, commencing in 1943, confronted an unforgiving landscape where half-tracks initially appeared entirely impractical. This challenging environment comprised impenetrable dense jungle, constricted and treacherous trails, expansive swamps, and numerous unbridged rivers. Nevertheless, resourceful Marine and Army units ingeniously discovered novel and effective applications for these vehicles. Demonstrating remarkable innovation, engineers on the ground undertook drastic modifications. They completely detached the front wheels from certain M3 half-tracks and ingeniously extended the existing tracks forward. This radical alteration effectively transformed them into fully tracked vehicles, which boasted significantly reduced ground pressure, a crucial advantage for navigating treacherous swampy terrain. These monstrous, field-engineered creations, while appearing utterly bizarre, possessed an uncanny ability to traverse deep, clinging mud that would utterly immobilize any other form of transport. During the Philippines campaign of 1944 to 1945, Japanese forces first encountered American half-tracks, and their reaction was one of genuine bewilderment. Japanese military doctrine, fundamentally, prioritized the deployment of light tanks and highly mobile, truck-borne infantry, leading them to perceive half-tracks as unduly intricate and demanding in terms of upkeep. Their assessment was not without merit. In the oppressive tropical climate, the sophisticated American and German half-tracks indeed necessitated incessant maintenance. The pervasive humidity relentlessly corroded vital electrical connections. The ubiquitous jungle mud relentlessly infiltrated every bearing and articulation point, and decaying organic matter frequently obstructed crucial cooling systems. Consequently, units deployed in these challenging environments quickly adopted a rigorous schedule of twice-daily maintenance, which often amounted to a virtual reconstruction of critical vehicle systems every few weeks, simply to keep them operational. Tales of remarkable adaptation also emerged from the fate of captured vehicles. The Soviet military, for instance, seized hundreds of German SD, KFZ, 251 half-tracks during the pivotal offensives of 1943 to 1944. Despite facing critical shortages of appropriate ammunition and spare parts, these captured machines were immediately pressed into active service. Resourceful Soviet crews often welded on supplementary armor plates, meticulously scavenged from the wreckage of destroyed tanks, thereby fashioning what could only be described as Frankenstein vehicles, heavier and slower, yet significantly better protected. A number of these Soviet-operated Hanemags underwent even more dramatic transformations, receiving entirely novel armaments such as potent 85mm recoilless rifles, formidable Katyusha rocket rails, and even terrifying flamethrowers. While such radical modifications would undoubtedly have appalled their original German designers, Soviet military doctrine unequivocally prioritized the maximization of raw firepower above any considerations of mechanical originality or purity. Operations in the vast, arid expanses of North Africa necessitated a distinct and equally extensive array of modifications. The omnipresent, fine sand proved insidious, infiltrating every mechanical component and drastically accelerating engine wear, reducing their operational lifespan to a mere fraction of what was typical. British forces, employing American M3s during the Western Desert Campaign from late 1942 onwards, countered this by installing colossal air filters, some towering almost 3 feet high, specifically to safeguard engines from the damaging ingestion of sand. Furthermore, they swapped the standard tracks for specialized desert pattern variants, characterized by wider blocks designed to enhance flotation and prevent bogging down in soft sand. The availability of water emerged as an absolutely critical factor. Vehicles traversing the unforgiving Sahara frequently carried additional radiator coolant and, quite often, towed trailers laden exclusively with water cans, serving the dual purpose of replenishing both the vehicle's systems and sustaining their crews. The profound overarching lesson gleaned from these diverse adaptations was clear. The half-track was not a singular, monolithic vehicle, but rather a multitude of specialized variants, each meticulously evolved to endure the specific, brutal conditions of its assigned hellish environment. The factory standard version, without such bespoke alterations, would undoubtedly have succumbed to these challenges within a mere matter of weeks. As 1946 dawned, thousands of half-tracks lay dormant within motor pools, stretching from the familiar training grounds of Fort Knox to the battle-scarred cities around Frankfurt. Amidst this surplus, military strategists found themselves grappling with an increasingly awkward question: what precisely was to become of these hybrid machines? With the global conflict concluded, the stark, unforgiving light of peacetime scrutiny illuminated the half-track's inherent design compromises, making them utterly impossible to disregard. It occupied an ambiguous space, neither fully a rugged transport truck nor a robust combat tank, and in the nascent geopolitical landscape of the Cold War, this ill-defined middle ground suddenly appeared to be a perilous tactical void. The Korean War, spanning from 1950 to 1953, was initially envisioned as the half-track's triumphant resurgence. American forces diligently dispatched M3s to the rugged peninsula, anticipating a performance mirroring their success on the European battlefields. However, the Korean theater starkly revealed every inherent flaw that the exigencies of wartime production and deployment had previously obscured. The country's relentlessly mountainous terrain proved devastating to transmissions and suspension systems that had been engineered primarily for the comparatively smoother European road networks. Furthermore, the standard rubber track blocks, which had functioned acceptably in the softer conditions of France, rapidly disintegrated upon contact with the abrasive Korean granite, often failing after a mere 400 meters of travel, necessitating constant replacement. The demands for maintenance were nothing short of exorbitant. A solitary M3 half-track typically required an astonishing 40 man-hours of upkeep each week merely to remain functional, a stark contrast to the approximate 10 hours needed for a conventional truck. Consequently, field commanders increasingly opted to abandon these temperamental vehicles in their motor pools, instead prioritizing the requisition of more reliable trucks. Yet, the decisive factor in the half-track's ultimate demise was its profound tactical inadequacy. The nature of combat in Korea evolved to feature significantly longer engagement ranges than initially anticipated, with infantry skirmishes frequently unfolding across distances of 600 to 800 yards, a stark departure from the close quarters, hedgerow fighting characteristic of Normandy. The half-track's meager 6.35 mm side armor, which had offered only marginal protection against rifle rounds in 1944, proved utterly ineffectual against the more potent, Soviet-supplied weaponry wielded by North Korean and Chinese forces by 1951. Even the relatively common PPSH-41 submachine gun, firing at 7.62 by 25 rounds, possessed the capability to puncture these thin armored sides from a range of 200 yards. Confronted with heavy machine gun fire, half-tracks were swiftly transformed into a perforated mess, akin to Swiss cheese. Commanders quickly absorbed the grim lesson, deploying M3s anywhere in proximity to the front lines invariably resulted in significant casualties among their personnel. Concurrently, military engineers were hard at work conceptualizing a truly revolutionary vehicle. The M113 Armored Personnel Carrier, officially unveiled by the Ordnance Tank Automotive Command in 1956, embodied a complete repudiation of the half-track's design philosophy. It was fully tracked, eschewing the hybrid wheel and track configuration. It featured aluminum armor, which offered equivalent protective capabilities to steel while significantly reducing overall weight by half, and crucially, it possessed inherent amphibious capabilities. Most importantly, its entire design originated as a dedicated personnel carrier, rather than being an adaptation of an existing truck chassis. This innovative approach meant the M113 could effortlessly traverse rivers, offer superior resilience against mine detonations compared to half-tracks, and its reduced silhouette presented a considerably smaller target on the battlefield. The initial production units of the M113 began rolling off assembly lines in 1960, and by 1963, the undeniable truth was evident. This new platform represented the vanguard of military transport. The fundamental engineering philosophy had undergone a profound metamorphosis. Half-tracks, in retrospect, were products of 1930s conceptualization, an approach that essentially involved grafting tracks onto established truck technology, with the hopeful expectation that the composite design would prove effective. In stark contrast, the M113 was the epitome of modern systems engineering. Its development commenced with a meticulous analysis of mission requirements, followed by the integrated design of every individual component to function cohesively, all optimized for the rigorous demands of the contemporary combat environment. Powering the M113 was the robust Detroit Diesel 6V53 engine, generating a formidable 215 horsepower. This represented a substantial increase of nearly 50% more power compared to the venerable Hercules engine found in the half-track, all while being lighter and operating on diesel fuel rather than gasoline, a significant advantage in terms of both safety and fuel efficiency. Furthermore, its advanced torsion bar suspension system offered a markedly superior ride quality and demanded considerably less routine maintenance than the older, less sophisticated vertical spring system employed by the half-track. Ultimately, a meticulous cost analysis delivered the coup de grace to the half-track's operational viability. By the early 1960s, the financial burden of maintaining the dwindling fleet of half-tracks still within the U.S. inventory had become prohibitive, costing more per vehicle mile than the procurement of brand-new M113s. Spare parts for the aging machines were growing progressively scarcer, a direct consequence of their production having ceased entirely in 1945. Compounding this challenge, the generation of mechanics proficient in servicing the intricate white motor transmissions were steadily reaching retirement. In stark contrast, M113 production was rapidly escalating, leveraging advanced modern manufacturing techniques that significantly reduced per-unit costs to below $40,000, a considerable sum in 1960, certainly, but an economically sound investment when weighed against the escalating expense of merely keeping 15-year-old vehicles operational. The narrative unfolding in the international defense market echoed this sentiment precisely. Israel, for instance, procured hundreds of surplus American half-tracks during the 1950s, deploying them extensively and effectively through the crucible of the 1967 Six-Day War. Yet, even this tenacious user nation had begun transitioning to purpose-built armored personnel carriers by the 1970s. Soviet military forces, after the conclusion of World War II, completely eschewed further half-track designs, moving directly to fully tracked APCs such as the formidable BTR-50. The French military retained their half-tracks for the longest duration, operating some well into the 1970s within the context of their various colonial conflicts, primarily driven by economic constraints that precluded a widespread, immediate replacement program. Ultimately, the obsolescence of the half-track was not attributable to a catastrophic failure on the battlefield. Indeed, these vehicles served their purpose adequately during their operational lifespan. Rather, their demise was a consequence of relentless evolution. The very nature of warfare had accelerated, its destructive force intensified, and it increasingly mandated highly specialized tactical solutions in lieu of generalized compromises. The advent of the M113 and its subsequent progeny exemplified this shift. They possessed amphibious capabilities, offered comprehensive NBC, nuclear, biological, chemical, protection, could mount significantly heavier armaments, and, most critically, they were designed to safeguard infantry personnel in an age dominated by pervasive automatic weapons and precision artillery. By 1970, virtually every advanced military establishment had converged upon the same inescapable conclusion. The choice lay unequivocally between dedicated tracks or dedicated wheels. The era of the hybrid vehicle had conclusively drawn to a close. The curtain fell decisively on a particular chapter of military vehicle design, marking the definitive conclusion of what could be termed the hybrid era. This pivotal moment saw the final American half-tracks gracefully exit active service around the year 1964, bringing to a close a commendable operational tenure that had spanned an impressive 23 years. These versatile machines, characterized by their distinctive wheel and track combination, had served with distinction across various theaters, embodying a design philosophy that sought to blend the speed of wheeled transport with the off-road capability of tracked vehicles. Their initial withdrawal from frontline roles, however, did not signify an immediate end to their utility. Rather, many embarked on subsequent, specialized careers within the military apparatus. Indeed, a significant number of these robust platforms were repurposed, finding renewed purpose in a variety of auxiliary functions. Some were ingeniously reconfigured as essential engineering vehicles, assisting with construction and battlefield preparation, while others transitioned into vital recovery trucks, capable of extracting damaged equipment from challenging terrains. A portion were even transformed into mobile command posts, providing crucial communication and coordination hubs away from immediate danger. Yet, despite these specialized second lives, the iconic classic personnel carrier configuration, which had once been a ubiquitous sight, vanished entirely from the rosters of frontline units. Today, the surviving examples are a rare sight, predominantly residing within the hallowed halls of military museums or meticulously maintained in private collections, serving as tangible mechanical fossils, poignant reminders of a bygone epoch in automotive and military engineering. These venerable machines stand as testaments to an era when design engineers harbored a perhaps overly ambitious vision, the fervent belief that, with enough ingenuity, it might just be possible to construct a single, universally capable vehicle adept at performing every conceivable task. Ultimately, this comprehensive ambition proved unattainable. No single platform could truly master all roles without significant compromises. However, for a critical and desperate decade, a period characterized by urgent global conflicts and an immediate, pressing demand for highly mobile infantry, the half-track's inherent imperfections, and its unique compromise of capabilities proved to be precisely what was required. Its ability to swiftly transport troops across varied landscapes, even if not perfectly, filled a vital operational void with remarkable efficacy. Stay with us and watch the end of the video. We will be grateful for your like and subscription. From London, it's fascinating to see how military engineering evolves, often with interim solutions like the half-track filling critical gaps before more specialized designs emerge. This historical perspective really highlights the pragmatic decision-making during wartime.